So you look at a massive, incredibly complex infrastructure project, right? And you've got to wonder, how on earth do thousands of intricate digital blueprints and wiring diagrams actually become a safe, functioning, physical reality? I mean, it's one thing to design a totally perfect system on a computer screen, but translating that abstract design into a tangible, high voltage system out there in the elements, that is an entirely different beast. Welcome to this explainer. Today, we're going to unpack that fascinating, incredibly high stakes bridge between pure theory and messy reality.
Okay, let's dive right in. Today we're exploring engineering reality, the principles of safe installation. We're going to take a really close look at how critical systems are physically fitted and brought to life, completely without compromising the safety of the folks building them or the end users relying on them.
Here's a quick look at our roadmap for today. First, we'll cover the actual definition of installation. Then, we'll talk about designing for the installer. Third, safety and high voltage. Fourth, the blueprint mandate. And finally, number 5, real-world field challenges.
All right, let's kick things off with Section 1, the definition of installation.
The baseline definition we're working with here is this. Installation is the physical fitting and connecting of equipment at pre-prepared locations based strictly on approved for construction designs. And I really want to emphasize that word strictly. Installation is absolutely never improvised. You don't just figure it out on the fly. It is an exact, methodical execution of a meticulously planned design. Simply put, if the blueprint isn't formally approved for construction, the physical work literally cannot begin. No exceptions.
Just take a second to think about the sheer scale of a vast station environment like this one. Think about the hidden architecture everywhere, the miles of cabling, the thousands of connection points, equipment housings scattered all over the platforms and tracks. Literally every single camera, departure screen, and signal requires meticulous installation planning. The physical space dictates the entire reality of the work, from signal sighting all the way down to cable containment and power supply constraints. It's like a giant puzzle where every piece has to be perfect. Moving on to Section 2, designing for the installer.
Try to put yourself in the shoes of a technician out in the field for a moment. On one hand, you have an absolute nightmare scenario. Imagine a cramped equipment case where you can barely even fit a wrench, let alone your own hands, and none of the wiring is labeled. That's not just annoying, right? It's a massive safety hazard that totally slows down operations. On the flip side, we see reality done right. Accessible modules, sensible, clear labeling, and fast changeover plug couplers. Those things make accidentally connecting a wire to the wrong circuit pretty much impossible.
This is exactly where ergonomic human factors come into play. And look, ergonomics in this context isn't about comfy office chairs. Out here, it's about survival and efficiency. Equipment absolutely must be placed in accessible, safe locations so a maintainer can physically reach into a location case without risking an injury. We also rely super heavily on fast changeovers. Those are facilitated by StageWorks and the plug couplers we just talked about, all to minimize the time workers have to spend in potentially dangerous environments.
Which brings us right to Section 3, safety and high voltage.
Now, these engineering rules, they are completely non-negotiable. High voltage cables must be correctly earthed, and all live electrical elements have to be fully covered to prevent any direct contact. But, it goes way deeper than that. Insulation specifications have to match not just the normal everyday operating temperature, but also the absolute highest potential voltages you'd see during fault conditions. And get this one is fascinating. Equipotential bonding. Without proper sheath gapping and bonding, transversal voltages can actually travel through telecommunication lines and cause what's called acoustic shock, which can severely damage a telephone user's eardrums. Seriously, every single technical decision here is literally protecting a life. Actually, it's not just electricity that poses a threat out there, it's chemistry too. For example, if standard PVC wiring is just allowed to rest against rubber-insulated cables, like PCP, the chemical interaction actually causes that PVC to become super hard and brittle over time, totally destroying the insulation. Designers have to literally plan the physical routing to keep them separated. Plus, when we're routing cables in confined spaces, like tunnels or subsurface stations, we absolutely have to use zero-halogen low-smoke sheathing. Why? Because if there's a fire, standard plastics produce lethal toxic gases. So the physical installation materials themselves act as a primary safety shield. Let's shift gears to Section 4, the blueprint mandate. Here is the mandatory, absolute flow of information. Step 1. The design gets finalized and stamped, approved for construction. Step 2. The engineering team hands the installation team precise drawings and explicit instructions. Only then, at Step 3, can the physical fitting actually begin. If the documentation isn't incredibly concise, clear, and complete, well, the entire commissioning process is completely compromised. So the real crucial point here is what we call configuration management. Installers must work from strictly version-controlled definitive design baselines. Imagine a huge construction site where the maintainers are working off version 2 of a drawing, but the testing guys are over there using version 3. It would be total chaos. The designer has to provide a definitive list of all applicable documentation so everyone on site is absolutely 100% certain they are installing and testing the correct, most up-to-date version of the system. But honestly, the burden isn't just on the installers out in the cold. The folks actually drawing the blueprints must have an intimate, deep understanding of the physical reality, the field rules, and the specific operating procedures of the environment they are designing for. If an engineer decides to use an off-the-shelf piece of equipment, they need to know for sure if it can survive high-induced voltages or crazy physical vibration. They have to anticipate the safety implications of failures well before a single wire is ever cut. And that leads us to our final section, number 5, real-world field challenges. The field is just full of these chaotic variables that you simply cannot simulate perfectly in a quiet design office. Installation teams are out there battling severe weather that can just halt outdoor construction dead in its tracks. They are constantly working in confined equipment rooms, literally bumping elbows with overlapping contractors who are trying to install entirely different systems in the exact same closet. They're fighting against incredibly strict, tight access time windows. And sometimes they're doing all of this while the physical environment around them is literally shifting, like when track realignment and structural building are happening at the exact same time. Because that environment is so incredibly unpredictable, the foundational design and those instructions must be flawless. But despite all that chaos, the final steps of the installation phase are still incredibly rigorous. First, there's a formal acceptance of the physical installation standards, basically double-checking that the mechanical work is totally sound. Second, there's a really painstaking correctness check of all the wiring against those version-controlled drawings we talked about. And only after these physical and wiring checks are completely passed is the plug-in equipment actually fitted, so that the formal testing and commissioning phase can finally kick off. If there is one core takeaway I really want you to remember from this entire explainer, it's this synthesis right here. The success of the physical world relies entirely on the precision of the paper it was drawn on. A safe, dependable infrastructure system? Yeah, that doesn't happen by accident. It is the direct result of designers accurately predicting the physical reality and installers meticulously, perfectly executing that vision. So, I'm going to leave you with this final kind of provocative thought to take into your own work. Will your next design survive the harsh realities of the installation environment? Have you really thought about the technician's hands, those weird chemical interactions, and all the chaotic variables of the real world? Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I will see you next time.